Start recording. Okay, so let's begin our homework 4. I have homework 2 up, so that's not a good start. So homework 4, we're just doing the Hall effect section for it. So it begins with this question. Honestly, the Hall effect is not too bad once you've gotten through it. The math involved is not that crazy. So anyway, so consider the setup shown in this figure. Current is flowing to the right through the semiconductor. A magnetic field is pointing out of the page. A voltmeter hooked up as shown reads a Hall voltage of positive 10 millivolts. Is this an N-type or P-type material? So to determine if it's a... I don't have my thing. Oops. Don't have the tablet. Also, I've been having a lot of issues with this tablet. I think I have to buy a new one. So if I have to restart OneNote a couple times, sorry about that. I will try not to. Okay, looks like it's okay right now. Okay, so to determine if it's well, there it starts already. And yeah, see, this is what's happened. I'm not pressing, and then it does that. Yeah, it'll stop in a second. I think I just have to restart OneNote and plug it back in. That usually makes it stop for a little while. Just acts up for a bit. Yeah, there we go. Okay, so for it to be an N-type, okay, this just means that the primary charge carrier, PC, well, okay, but, you know, I'll just type it out. Primary charge carrier is electrons, okay, and of course, if it's a P-type, that means that the primary charge carrier is the holes, right? So primary charge carrier is holes. So we just have to determine which one's the thing that's happening here, right? So the best way to do it is just assume, first of all, that it's holes and see if this makes sense, right? So if these are holes traveling that way, that would mean that, so I'll space away and try to do it. So think about how this is going to look. Go here. If I'm here and that way. Okay, so if our current is going this way, point your fingers in the direction of the current. The electric field is out of the page, so it should be like this for you, looking at you, but for me it would be like this. Okay, whatever, I'll just do it for me. So going that way, and then you curve your fingers in that direction, right? And your thumb is going in the direction of the force, the direction that those protons or holes would be pushed, right? So in this case, if we have it like this. So for me, if it's going to be going out of the page, so current out of the page, and that means down for me, right? For like looking at it like this. So yeah, out of the page down. So that would mean that our positive side should be here, right? Or the buildup of positive charge should be here. But if we look at the reading, it's telling us that there's a higher potential over here. So let me just say the blue is from the blue is what we're getting from this, is that it should be a higher potential here than it is down here, right? Because we're getting a positive reading, and so the positive goes to the positive and negative goes to the negative. And what that means is that this is an N-type.
So just to clarify, the velocity of holes is always in the direction of I.
Yeah.
But for electrons, it's the opposite. Okay, cool.
Electrons would be the opposite. Yeah. Exactly. Yeah. So there you go. Okay. So N-type for that. Let's look at the next question. Of course, anybody stop me if there's anything. This question, I should know the answer to this question, but I couldn't remember. Actually, this next question isn't really a Hall voltage question, but I think it's still interesting. If someone has a point to put in, I feel like I don't know how to explain this one properly, like super correctly. So all of these types of energies, can they be negative, positive, or only can they be negative or positive, or only positive? So kinetic energy can only be positive, and I know that because kinetic energy is equal to 1/2 mv squared. 1/2 is positive, m is positive, and v squared is positive. So kinetic energy has to be positive. Potential energy can be negative, and so by extension, I think total energy can be negative. So by negative, I mean like it can be negative, is what I'm trying to say here, right? Potential energy can be negative just because of a lot of definitions we put is just we say the system of two things have a negative potential energy. And that's like putting your zeros at infinity and all that. So that's my reasoning for that. It's not very sound reasoning. Like I think it's right, but I understand if someone's confused by that.
for why potential can be negative?
Yeah.
Well, we could also think of like back in PCS 211, we had negative GM1 M2 over R squared, and there's literally just a negative sign in front of it.
Yeah. That's what I was getting at. Is that a lot of times we define our 0 as infinity, so you put a negative there, right? Yeah, exactly. And so yeah, you have something like that. And then like a positive potential energy would mean that you need to do work to separate them more. Yeah, you need to do work to separate the two objects more. A negative potential energy would mean that you have to do work to push them together. I'm quite certain. Yes, that makes sense actually. So let me write that here actually. So a positive potential energy means you have to do work to separate the objects. Think about the potential energy between an object and the Earth, right? To separate it, you need to increase the potential energy, right? So you have to do work to separate them. But then that would mean that a negative potential energy means you have to do work to put the objects together. Which makes sense because think about like charges, right? Like charges are going to repel. So your 0 will be at infinity. 0 potential energy when it means when they're infinitely far apart. So to put them together, you need to do work, and so they have negative potential. There's a. I'm not going to answer B. There's just no point. So let's move on to 3. Of course, anybody stop me if you have any questions. We can do that. Otherwise, I'm sorry the quality's so low, but that's just what they gave in the question. So sadly, that's how it has to be. Okay, so a sample of silicon, I'm going to interchangeably, I think it's silicon, is doped with 10 to the 16 boron atoms per centimeter cubed. The Hall sample has geometrical dimensions. L is that, W is that, D is that. The current flowing through is that, and a magnetic field perpendicular to the current that has magnitude that. Find the Hall voltage, find the Hall electric field. So the first thing to note, textbook, there you go. The first thing to note here is that we need a picture. The question, there's a little prompt above, and it gives a picture that all these geometries are referring to figure 5.13 from the Neiman book. So let's go to figure 5.13 from the Neiman book. And Hall effect, and there we go. So that's 5.13. I gotta remove. I have a bunch of my PDF of the textbook has just a whole bunch of highlighted stuff in it. Never seen that before, but that is what I got. So there we go. Okay, that's the geometry that they are talking about. I'll just put that there. That's fine. Okay, so what do we know? We know that, okay, there are 10 to the 16 boron atoms per centimeter cube. Now you have to remember, boron atoms are electron acceptors, right? So they have one less, I'm not making a mistake here. They have one less valence electron than your regular silicon. And so you have holes. This is essentially saying your density of holes. So this would be this would be P naught is P0 is equal to 10 to the 16, 10 to the 16 centimeter per centimeter. Per centimeter cubed. What am I doing? Per centimeter cubed. Is that right? I'm pretty sure that's right. Okay. Yeah. So again, boron it's always going to be boron or phosphorus. So phosphorus is giving more electrons. Boron is giving a hole, so taking one electron. And so your doping of boron atoms is going to be your density of holes, right? It's the amount of holes you have per unit volume, because each boron atom gives one hole. Okay. The sample has geometrical dimensions. L equals that, W equals that, thickness D equals that. Okay, whatever. We'll deal with that in a second. I guess I'll just label it. well, actually, maybe I'll label it now. The current flowing is, I'll write that here. The current flowing is 0.001 amps, and the magnitude of the magnetic field is equal to 0.035 Tesla. Okay. And so from here, we want to determine the Hall voltage. So I'll say goal is our delta VH, right? So we got to find an equation that uses delta VH, and so I'm going to go to my notes for this, and I'm actually just realizing something that don't download my notes yet. There is a mistake, and I have to fix them. I fixed it already. I just have to upload the correct thing. So if you just downloaded my notes today or something like that, download them again, because there is a mistake in it, and an important mistake. So I'll show you it once I upload it. So I'll just upload a new version right now. And there you go. Okay, so it is updated now. You can go to my website as usual, www.4.ca/notes, and you can pick up my notes there. And it is correct now. So if you just downloaded it, there is a mistake in them. So download it again, and it'll be fixed.
So Adam, I got a question about this boron sort of thing. So I see how it's a 1-to-1 ratio between atoms and holes. But I want to know, would there ever be a 2-to-1 ratio sort of thing?
I don't think so. They'd have to give you an element with 2 valence electrons, and I think it gets more complicated at that point. I don't think you can just do that. So,
okay.
I think you won't get that. Okay, so we got to find some equations that include your this guy. So if I go to my notes, I can see I have this equation, which is nice to see. So it includes your electric field, that's your magnetic field. That should be a magnitude of the vector. So not really a typo, but oversight. But we're looking for delta VH. So let's see if we can figure it out from this. So that would imply to us that delta VH is equal to, there it goes, BI over NQD. Okay, where D is the thickness of the semiconductor in the direction of the magnetic field. Okay, so I'm going to write that here. D is the thickness of the semiconductor in the direction of the magnetic field. Okay. Lowercase d. But will I correct it? No. Okay. And then I is current, B is magnetic field, N is the concentrate. No, that's the P0. That N is just the number of.
It's the concentration of the charge carriers.
So shouldn't it be? Oh, it's the concentration of the charge carriers.
Yeah. So which would be P0 in this case because we're talking about a P-type, but it would be N0 if we're talking about an N-type.
Okay, so N refers to the concentration of the primary charge, or majority charge. Majority is probably the word. Majority charge. I can't spell. Charge carriers. Okay. Okay, so we know all this information, so I can just plug this in. I'm quite certain. So 0.035 Tesla, current in amps, I think is fine. So so that should be fine there. This is our P naught, so it's going to be 10 to the 16. Q is the charge of our hole, so that's just going to be E. Yeah. Yeah, okay. And D is the thickness of the semiconductor in the direction of the magnetic field. So let's take a look here. Magnetic field perpendicular to the current. So perpendicular to the current, which is like this, right? So like that. I guess that could be perpendicular as well. So that's not super. Well, it's along the thickness direction. So D. So 0.001 centimeters. Do I have to switch that to meters? Yeah, I probably do. No, it's already in centimeters here. Maybe I have to switch this to meters. Yeah, this is going to be confusing. Yeah.
Because Teslas are in units of meters, you either need to convert Tesla to centimeters, or you need to convert D to meters.
And also this to meters.
Yeah, that's true. Yeah.
That too. Yeah. Okay. So let's convert this to meters now. I'm just going to do that here. So we have 10 to the 16 per centimeter cubed. I want to have meters cubed. So, well, I'll do like this. So centimeters, and then in 1 meter, there is 100 centimeters. And then just cube that. So there you go. I just got to do 10 to the 16. 10 to the 16 times 100 cubed. So I get 1 times 10 to the 22. So this is equal to 1 times 10. So I'll just say 10 to the 22. Meter inverse cubed. There you go. Okay. So then now I'm going to put that there instead. So it's going to be 10 to the 22. That's fine now. It's the meters is right. And then Q is our E. And then D is the thickness in the direction of the magnetic field, which is just D. So in meters, that's, you just multiply by 100. I forget now. No. Yeah, you multiply by 100. Wait, 0 centimeters. And then it's going to be meters over centimeters 1 divide by 100. Okay. Yeah. So 0.001 divided by 100. Don't want to get it wrong. 0.0004. So 0.00004. 01. There we go. Okay. So we have that. That's just something I can plug in, I think. Let's see. So it's 0.035 times 0.001, and then I have 10 to the 22. So 10 to the 22 times, and now you got to remember what E is. So it's 1.607 times 10 to the negative 19. I think I remember that right. Times 0.0000. So I got my Hall voltage should be 2.18 millivolts. And should have the answers. 2.19 millivolts. Okay, good. That worked.
Okay, I got a question. Just when we were doing that conversion for PO. So I want to know, because it was cubed. Oh wait, in this case, because I was thinking that like multiplying it by 1,000 centimeters per 1 meter, because it's in this case would it be 10 times 10 times 10 instead of just like, for example, the regular 10 like raised to the power of something. Because you know when you're converting from anything raised to the power of like some sort of like raised to the I'm gonna explain it. 10, like for example, 10 centimeters. And then you need to convert it to 10 meters, right? You would do multiply by 10 raised to the power of something. But in this case, if it's like centimeters squared, you'd multiply by 100 raised to the power of that same thing. But in this case, it's cubed, so I was thinking that multiplying by 1,000 instead.
I think the best way to think about it is just that I want to convert meters cubed into something else, right? Into particularly into well, sorry, I should be clear. I'm trying to convert 1 over meters cubed into 1 over centimeters cubed, right? So the only way to get that variable there is if I cancel the meters cubed. So I want a meters cubed on the bottom. It should be clear. Okay. I want centimeters on the bottom, and I want to get rid of meters, but I need 3 of them. Right? I need 3 of them up here and 3 of them down here. Right? But it doesn't quite work like that because the actual conversion factor is 1 meter has 100 centimeters. Right? So this is backwards from what we were doing in the question. But you see here, I'm just going to do, so if you were to do it the other way, it would be just flipped over. But does that make sense? All I'm saying is just that if I want to get rid of this variable, right, I need that variable on the top. How many times? 3 times. So just do the conversion factor and then put it to that power. Does that make sense?
Yeah.
That's sort of the way that I think about doing it. They're variables. You can just treat all the units like variables, and then you're getting rid of the variables. Okay. It's just that it's a conversion factor, so you need to take into account the number there. It's not just 1 over 1, right? But yeah. So does that make sense?
Yeah, we're good.
Okay.
Thank you.
Okay. So there's that question. Now we need to do the Hall electric field. So I'm just going to find an equation that says something about the Hall electric field and see if we can figure it out. Let's see. The Hall electric field is equal to the drift velocity times the magnetic field. Okay.
Can't you just divide the voltage by the length?
Yeah, probably can do that. Yeah, that makes sense. So the Hall electric field is in the direction of the voltage, and electric field is, so magnitude of this for part B, is in volts per meter. So we know the volts and we know the meters. So there we go. That's all we need to do. The voltage is 0.00218 volts, and then the amount of meters, well, we need in the direction of the Hall electric field, right, which is this way, not this way, but this way, right, and that direction is W, so that's going to be 0.01 centimeters, which is 0.0001 meters. Okay. 0.00218 over 0.0001 is 21.8 volts per meter. Let's see if that's right. 21.88. Yeah, there we go. Okay, good. That was useful. So we have that. Number 4, we can move on to, unless anyone has any questions. Move on to here. And the same picture, so we don't need to copy that. So here's the first part of the question, and there's the second part. Okay. So a germanium sample is doped with a concentration of that many donor atoms at that temperature, at standard room temperature. So when they tell us it's the temperature, it'll always be that temperature. If it's not that temperature, then we don't have to do like certain calculations with it, because this table, the table that we have in the semiconductor book, let me find it quickly. I forget where it is. At the back, I think it's Appendix B. Yeah, it's Appendix B. This table is for 300 Kelvin. And I think we're always going to be at 300 Kelvin. Well, I mean, at this moment, we're always going to be at 300 Kelvin. So anyways, yeah, we'll need this table. And again, it is 300 Kelvin. So just that, don't worry about the temperature. The dimensions of the sample are that, and that. The current flowing is that. And the applied voltage is that. The magnitude of the magnetic field is that. Determine. Let's see what we got to determine. Oh, I don't want the answers just yet to show. So let me just grab it quickly without the answers showing right there. Whoops, I went to circuits. And then we can continue. Where are we? 4. There we go. Also see where the questions end for the Hall voltage stuff. Gallium. Just 2 more questions. That's it. No, there's more. Okay, whatever. There's 3 more questions. Whatever. Okay. So we need to determine. Where are we? This one. Determine this. Okay. Determine this. The Hall voltage, the Hall electric field, which we know how to find from the Hall voltage, and the majority carrier mobility. So again, I'm going to put the picture up just so we have a little bit of a visual of what's going on here. And I'll just highlight all the things we know. Right? So we particularly know the values of, well, we know the depth, the width, and the length. We know the current. We know the magnetic field. We know I don't even put the magnitude. We know everything about the magnetic field. And we know the actual delta V. Not delta VH, but we know delta V, right? Which is the potential difference across these 2 nodes of the semiconductor, right? Not these 2 nodes. That's the Hall voltage. These 2 nodes of the semiconductor are the voltage that we know.
We also know NO, right?
Yeah. Not directly from the question, but yeah. Right? Oh, never mind. We do know directly from the question. Yes, I didn't read that. With a concentration of that many donor atoms, right? So donor atoms means they are giving an electron, which means we have NO, right? And so NO is going to be 5 times 10 to the 15. With a concentration, that's probably meant to be per centimeter cube. That's what's probably meant to be negative there. Yeah, that doesn't make sense otherwise. Right? Someone agree with me? That looks like it's supposed to be.
I agree with you.
Yeah, you're not alone.
Okay,
I
good.
agree.
Yeah,
Good.
yeah, yeah.
Okay. So I'll just put that there per centimeter cubed. Everything's in centimeters. Tesla. Okay. Hall voltage. Hall voltage we can find from an equation, or can we find it? I mean, we probably from an equation. So first of all, majority carrier mobility. So the majority carrier is definitely electrons, right? So majority is electrons. So just at least have that visual in your head. Okay, so the Hall voltage, we'll just use an equation, I guess, that we know. I guess the same voltage as the same equation as last time, I mean. We know the... oh, no, we can do... I see.
The same one, can't we?
Yeah, we can use the same one, yeah. We can. Yeah, we can use the same one as last time. I was just looking at to do part C. There's another equation to do there. Okay, so that is the equation we use for this part. We're solving for delta VH, so delta VH is equal to BI over NQD. Again, D is the width in the direction of the magnetic field. N is the concentration of the majority charge carrier. So we can plug everything in. This is going to be 0.05 Tesla, but I can leave the Tesla out. We know we're in Teslas. And then current is just going to give you 250 microamps. So that's 250 times 10 to the negative 6 amps over. And now N is our concentration of our majority charge carrier. So that's, I'm going to have to convert that to meters, right? So 5 times 10 to the 15 over centimeters cubed. Well, the conversion factor is going to need a meters on the top, a centimeters on the bottom. In 1 meter, there's 100 centimeters. And we need to do that 3 times for the cubed. That is the wrong way. So we need a centimeter on the top and a meter on the bottom. Sorry about that. Hopefully, if anyone was confused, they didn't click away right at that moment. So there we go. And now it is going to give me the right thing. Yep, that's fine. So now that will just be 5 times 10 to the 15 times 100 cubed is 5 times 10 to the 21. Do that 5 times 10 to the 21 per meter cubed. So now I can just plug that in. 5 times 10 to the 21 per meter cubed times E, the charge of our, actually negative E. So negative E. That's the charge of our majority charge carriers, electrons. And then D is the thickness in the direction of the magnetic field, which is that many centimeters. So 5 times 10 to the negative 3 centimeters. But I want that in meters. In 1 meter, there's 100 centimeters. So just divide by 100 there. So 5 times 10 to the negative 3 over 100 is 5 times 10 to the negative 5, obviously. 5 times 10 to the negative 5 meters. And so I'll put that here. 5 times 10 to the negative 5. I leave out units here because it's going to get messy with units there. But just, that should be across. But just know that like everything should be in meters. Just do everything in meters. So if you have centimeters, just right away convert it to meters, and then you don't have to worry about it. Right? Okay, so just plug that into my calculator and see if I get the right answer. 0.05 times 250 times 10 to the negative 6 over 5 times 10 to the 21 times negative 1.607 times 10 to the negative 19 times 5 times 10 to the negative 5. And I get delta VH is equal to negative 3, negative 4. So negative 0.3111 millivolts. Let's see if that's correct. Negative 0. Yeah, pretty much. Okay. Then that's for part A. So I'll stop for a second. Any questions? Sounds like we're good. Oh, I just realized something. I should check if, yeah, checking my voices in the recording. That would be bad. Okay, so that is part.
Yeah, no, actually, I do have a question.
Okay, yep.
It more just has to do with the units. So
Okay.
depth would just be like almost like kind of the height. So there's length, width, and height.
Mhm.
So my question is, why is it per centimeters cubed? And then, for example, width is per centimeters squared, and so on. Like, why is it different units like that?
What do you mean per centimeters? Oh, like
So
this
yeah,
like these exponents here?
exactly. So you see how it's -3 and then -2, then
Be careful.
-1.
That's not on the centimeters. That's just saying 5 times 10 to the -3 centimeters. 2 times 10 to the
Oh,
-2 centimeters.
yes. Okay. I was gonna say because. Okay. Yeah. Yeah. Okay, that
Makes
makes sense
sense?
now. Right.
Yeah,
Yeah. Yeah.
I understand. It's like it's weird to see the exponent there. It's not denoting the type of unit. It's just denoting the magnitude.
Yeah, because I was thinking of like, for example, whole sort of concentration. So where the -3s are on the right of the centimeter.
Yeah,
So I just
yeah,
kind of made that mistake. Okay,
yeah,
we're
yeah,
good.
yeah. It's just a visual thing there. Yeah, makes sense.
Sir, Adam.
Yeah.
So I've used like all the same values. I converted to centimeters everything instead of meters, and I'm getting 0.3125 millivolts instead.
0.3125.
Which is confusing because all of my what's it called? Coefficients to the exponents are all the same as yours. Do you like
Um,
is that what's written as the answer in the homework problems? 0.311?
312 is the answer. But if you
Okay,
have
whatever.
two, yeah, it's
Yeah, okay, fair enough.
pretty close. Yeah. But you're doing everything in centimeters.
Yep.
Yeah. I mean, obviously it works, but just Tesla. I thought Teslas would screw that up. because we're in
Teslas
Tesla.
have to be converted.
To centimeters.
Yes.
So
But
Oh,
like
and
you
you're
divide
and
by-
you converted Teslas to highlight the
yeah,
wrong T there.
because
but-
then you only have to convert one thing, and I just
yeah. I just don't know how to convert Teslas. That's why I'm doing
Yeah, fair
this. How do you do it? How do you convert Teslas?
What I do is just divide by 10 to the 4.
Yeah.
Divide by 10 to the 4. Okay.
Yeah.
There we go. I'm sure. Obviously, there's a reason, but
10 to the 4, or otherwise known as 100 squared. If like you take units conversion and yeah, just get used to doing units conversions consistently.
yes, of course. Yeah, like we did it here. Good. Okay, so yeah.
I was just gonna say that because I think is this the last hall voltage question, or is there one more after
No,
this?
there's more after this.
Okay. The one thing that they like to ask during physics questions is usually like some kind of like, hey, if we changed this variable but all other variables stayed the same, how would the hall voltage change or something like that?
Yeah.
So just there's like a slide full of equations or something somewhere. Just make sure you sort of understand like the what do you call them, proportionalities between each things, because I've seen questions where it's like, we change the magnetic field, how does that affect the hall voltage or something like that.
Yeah, exactly. So yeah, that they probably will give us a question like that. Do we know how many questions are on it? Yeah, I know they're annoying. Do we know how many questions are on the midterm?
I don't think they told
it's
us.
8, right? I thought it was 8 on the midterm.
Oh yeah, 8, 7 multiple choice and 1 long answer.
Oh, one long. Oh yeah, I forgot about the one long answer. Yeah.
Wait, no, aren't they all long answer? You have to write down all of your answers.
Yeah,
Wait,
but it's like
I thought it's the other way around. I thought there's 1 multiple choice and then 7 long answer.
no. So my
Oh,
understanding
that'd
is
be
it's 7 multiple choice, 1 long answer, but at any point, so you have to submit your solutions for all of it, but they don't mark your solutions for the multiple choice questions. They can choose to look over them, and if they say, "Hey, what you wrote down here doesn't back up your multiple choice answer," then they just give you a 0 for that question.
Yeah, I see.
It's like an anti-cheating method. It's not actually meant to like mark your
So they may
process.
as well at that point just give us partial marks for questions that we deserve partial marks on. I understand that takes longer for TAs, but
She already said no, don't worry.
yeah, I'm sure. So there we go.
A question.
Mhm.
What is this grading system? It says it says it has 8 questions, but it says the total mark of the test is 10 points.
Yeah, so 3 points for the full solution and 1 point for each of the multiple choice questions. It says right below.
There you go. There's your answer. That's how the grading system works.
Okay. Gotcha.
There we go. Okay, to find the Hall electric field, we just take the voltage across these two nodes, which is the Hall voltage. So that's going to be negative 0.3111. And actually, I'll just do it in actual volts. So negative 0.0003111 volts per meter. And how many meters is that? That's W. W is 2 times 10 to the negative 2 centimeters. So 2 times 10 to the negative 2 centimeters. So I want that to be in meters. And 1 meter has 100 centimeters. So that's going to be 2 times 10 to the negative 2 over 100, which is 2 times 10 to the negative 4, of course. So 2 times 10 to the negative 4 meters. 2 times 10 to the negative 4 meters. And this will give us our electric field. So negative 0.0003111 over 2 times 10 to the negative 4. So I get negative 1.5556.
So it wouldn't always be the width, right? For a Hall voltage device.
Well, it'll always be W in this picture.
Yeah, in this specific picture. Okay.
Right? Yeah.
Yeah.
That's not the answer, strangely. Okay, let's see what happened. That is delta V over M. Delta V is that. That is our delta V. Did I convert this correctly?
What is M? What is M?
M is the
Per meter. Yeah.
per meter.
No,
Yeah,
that is right, but you just have the answer in per meter, but the answer is in per centimeter.
Oh, the answer is in per centimeter. Okay, so negative 1.5.
But you do have a negative sign though, which is weird.
That's true. So is it just, do I just take the absolute value of the voltage? Let's see if we get the absolute value, right? Volts per meter times meters per centimeter. 1 meter has 100 centimeters. So answer divided by 100. Yeah, of course, I should have just paid attention. Negative 0.015556 volts per centimeter, which is correct. Except the negative sign. So I guess you just take the absolute value of it. Because
I think it's because it's the magnitude of the electric field.
Yeah.
Yeah.
The magnitude is already absolute.
Yeah, the magnitude is just positive. So that should be, I guess the actual formula is not that it's V over M, but it's the magnitude of V over M. Probably what the actual formula is. So, yeah, there we go. So just remove these guys. Okay. So the majority carrier mobility can be determined using just an equation that was given to us right here. It's this equation right there. Everything we know. Plug everything in. So current was 250 microamps. So 250 times 10 to the negative 6 amps times L. L is so 0.1 centimeters. 0.1 centimeter. 0.1 centimeters? Yeah. Which is 0.001 meters. Okay. Unit conversions. And then we have, I guess okay. If anyone's confused, I'll put units, but no one's confused then. NO is 5 times 10 to the, but we converted it, so it's 5 times 10 to the 21 per meter cube, so 5 times 10 to the 21. The width, W, is 2 times 10 to the negative 2 centimeters, so divided by 100 is going to be 2 times 10 to the negative 4. So 2 times 10 to the negative 4. D is thickness in the direction of the field, so that's going to be this one. Here, 5 times 10 to the negative 5. 10 to the negative 5. Q is but absolute value, so it's just E. And delta Vx is the voltage across the actual given thing. And that voltage is 100 millivolts, so 0.1 volts. Now we plug all this into the calculator. So we get 250 times 10 to the negative 6 times 0.001 over 5 times 10 to the 21 times 2 times 10 to the negative 4 times 5 times 10 to the negative 5 times 1.607 times 10 to the negative 19 times 0.1, and I get this is 0.3111.
Adam.
Yeah.
Why is it the applied voltage instead of the Hall voltage? Can you talk about that, or like?
Yeah, like where the formula comes from?
Yeah, I guess if that's okay.
Let's see. I don't know if I particularly know exactly where the formula comes from, but we can look at the slides and see if we can figure it out there. Let me just see. As long as you can find the mobility thing, I think you combine some equation here. Obviously, a lot of it comes from.
Or here, maybe could you like scroll up to the picture and we can try and like the diagram, because if it's moving across L, right?
It's moving in the direction of L, yeah. And so the voltage across there is L. Is the applied voltage, I mean.
Okay, well that makes sense.
So then you would need that voltage to determine its mobility, because that's sort of what's helping it move.
Because the Hall voltage is perpendicular, so it shouldn't make a difference.
Exactly. Yeah.
Okay.
So
thank you.
Obviously, there's much more reasoning you can put into that, but yeah, that's a good explanation, at least for now. Okay, this is not quite. I mean, it basically is. Because if I just, this is in meters. Well, I'm just gonna. Okay, if they want units from us, yeah, I guess let me do the units here quickly, just so I can actually show what, because I don't know what the units of that is, you know, without looking at the answer. So, amps meters per meter cubed, meters, coulombs, volts. Okay, so obviously now that one of those cancels, one of those cancels. So we're gonna get amps 1 over meter squared coulomb volts. Okay, coulomb volt is a joule, and an amp is a charge per second, but I don't think we want to go to seconds. Do we want to go to seconds? Oh yeah, we do want to go to seconds.
Coulomb per second, isn't it?
Yeah, coulomb. That's what I mean. Yeah, coulomb per second. Coulomb per second over a coulomb volt. No, but I might want to leave the coulomb there because then it'll cancel. And a volt per meter. Yeah, okay. I'll leave the coulomb there because coulomb volt meter squared is gonna end up being C over S times meter squared over coulomb volt. That will cancel out. So it's going to be meter squared over second volt seconds, I guess. And that is what it's supposed to be. So that is the unit of our mobility. Meter squared per volt second. Okay, meter squared per volt second. And now the answer is just in centimeters for whatever reason. I guess because it was all given in centimeters. So centimeter in a meter. So 1 meter has 100 centimeters, but we want this squared. So we want to get rid of 2 meters. Not 2 meters, but the unit meter twice. So 0.3111 times 100 times 100 is, okay, I didn't have to do that, 3111 centimeters squared per volt second. Not exactly right, but pretty much right. Slightly off. 15 off. Strange. Yeah, that maybe I typed something in wrong here because I forget who said they did it in centimeters and you got 3125 or something like that. That is what they got. So maybe I just typed something in slightly wrong here. And we just got a little bit off. But it's the right method. That's all that matters. At this moment. That's all that matters. Okay, so we did that one. Silicon 3D geometry. There's question 5, question 6, question 9. Let's just keep going, I guess. Well, actually, it's 8 o'clock. It's 8 o'clock, so maybe we want to start. Let's do one more hall voltage questions because this one has another one like this. Let's do another hall voltage, and then that'll probably be enough hall voltage for now. And we can move on to just the other practice problems for the other sections. So I just think it's good to do hall voltage too because in the tutorial she didn't do any hall voltage questions. Oh no, she did. Never mind. What am I talking about? She didn't do something. I forget what she did. There was something I remember she didn't do. But anyways, that's fine. Let's still just do this last question, and that we'll move on to other stuff. So the Hall effect device is fabricated from silicon at 300K. The geometry of the device is all that. The electrical measure current is that. The applied voltage is that. The magnetic field is that. The Hall field is that and is in that direction. Determine the Hall voltage. Okay, and then all this stuff. Okay, that's fine. Good to have the picture. So there's the picture. So the Hall voltage, remember that we know that the magnitude of the Hall field is equal to the magnitude of the Hall voltage over what distance? This distance W, right? Because that's where the Hall field is over. So if I want to find the Hall voltage, delta VH is equal to the magnitude of the Hall field times W. And I know both of those things. So that's going to be, I don't even have to convert, 16.5 millivolts per centimeter times W is 0.05 centimeters. So 16.5 times 0.05, and I get 0.825 millivolts. So that's part A done. Interesting, they got negative. Points in the negative Y direction. So that would just be essentially from the next question. I don't think you'd be able to get negative just yet. That is the magnitude of the Hall voltage. You'd have to also answer this question to figure out that. Anyways, well, I guess actually, never mind. You don't have to do that. I'll just explain why. So this is pointing in the negative Y direction. So that would be this arrow. Let me just highlight it in red. So this is the arrow we're considering. Okay, that is our Hall field, right? So if the Hall field is going down like that, that means that that is the direction that hold on. That's the direction that protons. I would imagine that that's the direction that the opposite of the direction that electrons are being pushed. Why would electrons be being pushed that way? Just confused by something.
So we know that the Hall field has a magnitude of 16.5 pointing in the negative Y direction.
Yeah, that's the
And
right
if it's pointing in the negative Y direction, then that means that the bottom plate, so the plate closest towards us out of the page is negative, and the plate farthest away is positive.
Sorry, did you ask
because it comes from the positive side. Yeah.
Did you ask why E Hall points in the same direction? Like why E Hall points towards this positive side?
I guess I was just confused why the electron was moving this way, but now I understand that, yeah, it makes sense, because the E Hall is going to emit from the positive side. Yeah.
Also, I think of doing what's it, QV cross B, right? Current is going from the left side to the right side, which actually means that the electrons are going from the right side to the left side.
Yeah.
So if you do right hand rule and you flip it because it's an electron, it's the same direction regardless.
Yeah.
That's why it's always I cross B no matter what.
Makes sense. There you go.
So you see that symbol over there on the diagram where it says VH. You could think of that as a voltmeter, right? Just telling you where the
That is a
positive
voltmeter,
terminal.
yeah.
Okay.
Exactly. And okay, so then there we go. We know that the it's going this way. So that means that if it was going, so that's the positive plate there. Yeah, okay. So that means that this is the positive plate. The negative terminal is attached to the positive plate. That means we're going to get a negative reading. Negative. We're going to get a negative reading there. And again, that's because the negative terminal of V Hall is attached to the positive plate. We know that's the positive plate because it told us that the electric E Hall is in the negative Y direction, and the E Hall comes from the positive plate. Okay. Is the sample N-type or P-type? So, well, we can just determine here, essentially. But, well, we'll see. So we're going to get, let's assume it was positive charges. That means the positive, like, let's assume it was P-type. So the direction of our current is like this. Hall like curls up like that, and so our positive charges would come to the plate closest to us, but that's the negatively charged plate, so that doesn't make sense. So it looks like it's going to be an N-type. So it wouldn't be positive. I mean, it is negative, so it doesn't make sense for the charge to be positive. So yeah. The majority carrier concentration, we'll figure that out somehow. Majority carrier mobility is, again, this equation. So that's for mobility. That's for part C. For part D. Part C is the majority carrier concentration. Let's see, is there something I'm missing here? No, we know that. I think I can just take this equation and solve for N. Yeah, I think that's what I'm thinking. Yeah, so take this equation and solve for N. We get N equals, and now I gotta do a little bit of magic. So it's gonna be BI over QD delta V Hall. And now everything in whatever. So 0.065 Teslas times our current, which is 0.5 milliamps. So 0.0005 amps over Q, which is the charge of our majority, whatever. So it's negative E. Should that be an absolute value? I don't think so. That is supposed to be negative. D.
Well, I mean, it doesn't N have to be positive, so it doesn't matter the value of E.
Maybe, yeah, yeah. It's a concentration, so yeah. So probably it's supposed to be. Well, actually, no. This is what's gonna happen: is that delta VH is negative and E is negative, so that'll cancel out. Yeah. And then D is this distance like that, 0.005 centimeters. So that's going to be 0.00005 meters. So 0.00005 meters times delta VH, which is negative 0.000825 volts. Okay. So let's plug that in. 0.065 times 0.0005 over negative 1.607 times 10 to the negative 19 times 0.00005 times negative 0.000825, and I get my concentration is 4.903 per meter cubed. 4.902. Oops, I forgot the magnitude. I mean, I forgot the times 10 to the, that's an important one. There you go. Okay, and then just convert this to your, so I'm going to put that over here, per meter cubed. So I'm going to convert this. I want per centimeter now, right? In 1 meter, there's 100 centimeters. And I want to apply that 3 times. Okay, so it's going to be our answer divided by 100 cubed. And so I get 4.903 times 10 to the 15 per centimeter cubed. There. And now to find mu, we just do mu equals that. I mean, essentially, we just plug everything in. So, yeah. Let me look at just the next question, see if it's worthwhile doing. No. 9 might be worthwhile. Resistance, we like to increase resistance to that. Okay, let's do question 9, because I think it's okay if I just don't do this. You just plug everything in, and then you get the number. Is that good with everybody? I'll just move on to question 9.
Yep.
Sounds good. So let's take a look at question 9. Question 9 seems interesting though. You have a sample of intrinsic germanium, Ge, at room temperature, which is a cube of size that, of side length that, probably. The resistance of the sample is that. You would like to decrease the resistance to that. Okay, So let me just, again, we have a cube of the semiconductor, right? We have cube of semiconductor. There we go. And we know all the side lengths here, right, are all 0.1 centimeters. Okay. The resistance of the sample is 450 ohms. Okay. We would like the resistance to be that. So what concentration of donor atoms would need to be added to the sample to achieve this resistance? You may assume that mobilities are the same as those given in the table and that all donor states are fully ionized at room temperature. Okay. So let's find our table here. We're looking at germanium. Open this. There we go. Germanium. And we need this section. What's really going to be useful is just mobility. Well, I don't know about mobility. Possibly mobility. But intrinsic carrier concentration, right? So if I'll just take a picture of that and then just that so we see what I'm taking a picture of. And germanium is the first one. I mean, the last one there. So we additionally have these properties of germanium. Okay, we additionally know these facts. Okay, so I'll put that there. We would like to know what is the concentration of donor atoms needed to make the resistance equal to that. So the concentration of, we're trying to solve for this, concentration of donor atoms. Donor atoms give electrons, so it's N0. We're solving for that. That's what we're solving for, right? To make this here. The concentration of donor atoms will be much larger than Ni, so the doped material will be strongly N-type. Okay, so if the doped material is strongly N-type, I'm pretty sure, now someone correct me if I'm doing this wrong, that means that when we calculate the conductivity of a substance, we can just treat it as E strongly N-type, N0 mu N. There you go. Is that right? That's right. Yeah. Okay. The full equation is this. The full equation of conductivity is E N0 mu N plus P0 mu P, right? The concentration times the mobility, concentration times the mobility. But if it's strongly N-type, you can just say that's 0. Okay, and then we just get this equation here. Okay, so I'm just kind of building up some facts. This is another fact we know, right? This is not something useful. And this is our goal, right? This is our goal. So these are all facts we know. Okay, so right away, we're dealing with resistance. Whenever you're dealing with resistance, it's probably good to say R equals I over V, yeah. I over V, yes. Is that right? Yes. V.
No, it's the other way around.
No, it's the other way around. Yeah. No, because I equals V over R. So, yeah, V over I, yeah. R equals V over I. I swear I do take ELE, but I don't remember the way fractions go, apparently. Okay. So, we know this here. Okay, that's something. Let's see if there's definitely other stuff that I can include here. So I'm going to go to the current section. Oh, this is also equal to, now this is what might be interesting. This is also equal to the resistivity Did I not fix the typo? Okay. So the problem I had in my notes that was a typo is that I used the wrong symbol. I called one of these resistivity and one of these conductivity the wrong one. I could have just left it, obviously, because it's just a symbol, but that will be very confusing for the future, right? When you have to compare it to actual stuff from the textbook and whatever. So I tried to fix it. I think I might have left one. That's going to be rough. Okay. But I have it corrected there. So we have here, okay, first of all, also another fact we know, conductivity is equal to 1 over resistivity. Other way around. Resistivity is equal to 1 over conductivity. I mean, that's the same thing, but just I said it backwards. Okay, this is equal to conductivity, no, resistivity, L over A. Okay. L over A, we do know what that is, right? And 1 over, and this guy is 1 over that, and that is that, right? So I can just put that here. This is 1 over E N naught mu n. Right, so I can substitute that into here. R equals 1 over E n naught mu n L over A. And then I can just solve for the carrier concentration. And I didn't need this. I guess I just didn't need that. Yeah, I don't need the current resistance for some reason. Okay, maybe in the later part of the question we need it. So that's an L. And then again, because it's going to be R A over L equals 1 over E n naught mu n. Okay, that's what I'm solving for, right? That thing there. So I'll flip both fractions. So L over RA equals E n naught mu n. And then so we know now that the thing we're solving for, concentration of electrons, is going to be L over R A E mu n. Great. Okay, L is, do they want it in centimeters? If they want it in centimeters, I'll just leave everything in centimeters. They want it in centimeters anyways, so I think I can just leave it. I think that's all fine.
Okay, this is quite strange to me because we're trying to achieve a certain resistance, yet it's not even relevant in the actual equation or the evaluation. We don't use the 0.45 ohms.
We are gonna. That is what I'm gonna
Oh.
put here. That's what I'm gonna put here. This is what I mean. We don't need that.
Okay.
We might need it for the next these B and C. We will use 0.45, but that's what I'm gonna put in.
If the resistance of the sample is 450 ohms and you know like how far the distance is it needs to cross, you can actually get the resistivity in terms of centimeters.
The resistivity in terms, yeah.
Because it's just, if you know it's that many ohms per this many centimeters, you have your resistivity.
Yeah.
You can do this more ways than one, but like that's seems like the simpler way to do this.
Yeah, I'm trying to think of what equation. Yeah. Okay, let's continue with this one. But yeah. So L, can I leave everything in centimeters? I'm worried about leaving everything in centimeters. Is something going to screw up here? Amps is coulombs per second. That's fine. Mu is, that's in meters or something. Oh, and that's in centimeters actually. Okay, good. So just checking here, mu n is in centimeters squared. Okay, I think we can leave everything in centimeters. So
all the values from the textbook, I'm pretty sure, are always given in centimeters.
Okay, good to know. So 0.1 over 0.45 times the current. Current we don't know.
All right,
okay.
Adam, I want to just ask. So our final solution. So when we're finding our whole our electron concentration, it's going to be in centimeters, or per centimeters cubed. So why would we convert our units to meters in the first place to calculate that? Don't we want it in centimeters?
Yeah, we want it in centimeters. Yeah, I'm just worried because like SI units, I don't want to get the wrong answer because we just didn't convert a unit, right?
So what I'm saying is that even if we were consistent with, as long as we're consistent with like not having centimeters in one thing and then meters in another variable, it might mess up the output. But as long as we're consistent.
You have to be really consistent. So like Teslas, you have to turn that into Teslas in terms of centimeters.
Yeah.
Right? So like if you got a Tesla reading, and so it's little things like that that might not jump out at you. Like it wouldn't jump out at me that Teslas have to be changed when we switch to centimeters, right? So I'm just worried that there'll be other things that don't jump out at me like that I have to unit convert. So it's in my brain, it's easier to just convert everything to meters and then convert back to centimeters at the end. At least
So
I can be more confident in what I'm doing if I do that.
So for your last like expression that you're solving for right now, if you were to convert your mobility into meters, you would still get you wouldn't get the same output. You would just have to convert that back into the per centimeters cubed, right?
Squared. Like this here?
Oh yeah, sorry.
Squared. Yeah. If you'd get the same answer. In this case, it's fine because everything here is in terms of, there's no like Teslas and there's no like things like that. So like this is a length, this is a resistance, which is fine. This is an area, this is a charge, and this is a, we know the units. This is centimeters squared volt seconds. So it's fine.
Okay, okay. Thank you.
Okay, area squared is 0.1 squared times E. No, negative E. Negative E? Strongly N type, yeah. So negative E. But concentration has to be positive. So why are we getting a negative? Magnitude, maybe I'm just missing a magnitude. Is there supposed to be a magnitude in one of these that I'm missing? Okay, let's see if we get, if I just do absolute value, if I just say E, let's see if we get the right answer. And if we don't, then maybe that's the point. And then mu n is 390. And by 390, I mean 3,900, not 390. Okay. So 0.1 over 0.45 times 0.1 times 0.1 times 1.607 times 10 to the negative 19 times 3,900. I get 3.55 times 10 to the 16 per centimeter cube, which is correct. Okay. So there's that whole process. Just combined a bunch of facts. Yeah, okay. Okay. Next part of the question. What fraction of germanium atoms will need to be replaced by a donor atom to achieve this resistance? Okay. So in I need to compare it to Ni. So Ni is 2.4 times 10 to the, so let me write that here. So N0 of this new material is 3.55 times 10 to the 16. Ni is right here, which is 2.4 times 10 to the 13. And so to figure out the fraction of the original amount that needs to be converted, well, you want to say, let's see, you want to have the fraction, so converted per germanium. Yeah, per germanium. So I think you would do 3.55 times 10 to the 16 over 2.4 times 10 to the 13. See if that worked. 3.55 times 10 to the 16 over 2.4 times 10 to the 13. And the fraction is, well, that doesn't make sense. 1 out of every 2 million? That's not what I got. If I invert that, no, it's still not what I got. It's still 1 out of every 1.2 million. Okay. Let me think about that. The intrinsic is the number of, that is the concentration per centimeter cubed.
Sorry, what's the question again?
Centimeter cubed. There. What fraction of germanium atoms will need to be replaced by a donor atom to achieve this resistance? So definitely need to compare it to the intrinsic carrier concentration.
So,
but other than that, I don't know exactly how you need to compare it to it. Okay, so let me put the question here just so I don't have to scroll up and down.
wait, we could subtract the amount of extrinsic. So we could subtract extrinsic from intrinsic. So that's the amount that we need, right?
That is the amount of new. Yeah, that is the amount. So let me write that here. Yeah.
That's the amount of electrons that we need.
So I'll say new. What should I say? Additional concentration of electrons would be N0 minus Ni. Yeah, so 3.55 times 10 to the 16 minus 2.4 times 10 to the 13 is 3.5476 times 10 to the 16. So that's how many new, that's how many germanium atoms need to be replaced with donor atoms. So then we just take the total number of germanium atoms. Yeah, we just take the total number of, so okay, so this is the amount of new, is that the answer? Yeah, almost. I think it is. Times the 16. Yeah, that's it. Per centimeter cubed. That's the amount of new, the new electrons per centimeter cubed. And since we're all in centimeters, it's fine. That is the answer. Yeah. So that is the answer. The fraction of germanium atoms. Oh no, that's not the answer. Sorry, I was reading the wrong thing. We almost had it. That is not the answer. That's not a fraction, so makes sense that that's not the answer. The fraction of germanium atoms will need to be replaced by a donor atom to achieve this resistance. Wait a second.
And then do we take the total amount of atoms per centimeter cube and divide that by that value? Or something like that?
In the intrinsic?
No, the overall. So in germanium there are 4.42 times 10 to the 22 atoms per centimeter cube.
Oh, you found that in the table?
Yeah.
Oh, that's pretty good.
I feel like
Atoms per
that'll be
centimeter.
important.
That does sound important. 4.42 times 10 to the 22. 2 times 10 to the 22 atoms per centimeter cubed. Okay, that's how many we started with. That is how many new electrons we need in a centimeter cubed. So then I just divide these two. I think that'll work.
Because we need to replace 3.5476 times 10 to the 16 atoms with our... yeah, I think that makes sense, right?
I think that makes sense. So this is... Yeah, 1.2. It's upside down. So it should have been 4.242 times 10 to the 22 over 3.5476. And that would, let's put some units here. This is the number of, so this is the number of germanium atoms per centimeter cubed. This is the number of what?
Donor atoms, right?
Yeah, donor. So I'll say donor per centimeter cubed. This would get us donors per germanium. But I guess we wanted germanium per donor.
What's the original question?
Fraction of germanium atoms. What fraction of germanium atoms will need to be replaced?
That's kind of ambiguous, isn't it?
Yeah, it's a weird phrasing, but not. It's just we can't understand it. Yeah, fraction of germanium atoms will need to be replaced. What fraction will need to be replaced by donor atoms? So what is the fraction between the germanium atoms that are being replaced?
So that's donor over germanium, right?
Yeah, which is what we put, but the answer is the other way around. No, is it the other way around? Because it'll be.
Did you compute that?
Oh no, actually, no, that'll be fine. I think I maybe misinterpreted a little bit the calculator. Yeah. So that's approximately 1 over 1.2 million. There, that is the answer. Okay, we're good. Never mind. Yeah, donors per germanium. That is approximately 1 over. Because what happened is that I inverted the answer and I got 1.2 million. And I was like, oh, that's the right way. But no. It should be 1 out of every 1.2 million. And so that's correct. Okay. Difficult phrasing for that question, but that's about how you do it. Let's take a look at part C. And I knew this would be a good question at the end. Okay. If you decided to add acceptor atoms instead of donor atoms, would your answer to part A change? And now what was part A? What concentration of donor atoms needs to be added? So they're saying if we did acceptor ones. So that means we're looking for, yeah, it would change. It would change. Not really. but kind of, I guess. No, actually, it wouldn't change.
It would, because the mobility would be different for electrons versus holes, so it would change substantially, wouldn't it?
But remember that n0 n0 p0 is equal to ni squared.
Yeah.
So I could solve for p0 here, right? And then that would give me the corresponding one. But my result for n0 would not change. The answer to the question would be p0, right? And so yes, my answer to the question would change, but my result for n0 would not change.
What's question A again?
Question A is asking what concentration of donor atoms, so what n0, would be needed to have this resistance.
But if we look at our method for that question, we did R is equal to rho L over A, and rho is we the reason that what we came up with rho is 1 over sigma, where sigma is equal to En mu n plus P mu P. And so if we're adding holes, the reason that we discarded the holes in the original equation was because it was strongly n-type, which means that we don't have to worry about it. But if we're adding holes, then we can't focus on n mu n, and we have to focus on P mu P, right?
Yeah.
And if
It's
mu
not
P is-
about focusing on just on P mu P. It would just, you couldn't simplify that expression. You would have to know
Yeah.
the concentration of NO as well.
No, we wouldn't, because if we're adding donor atoms, we always assume that we're adding. So, oh wait, if we're adding acceptor atoms, then we assume that we're adding enough acceptor atoms that the amount of donor atoms.
So that's the
is relevant.
assumption. That's always the case.
I'm pretty sure, because if not, how can you solve the question?
Exactly. I think that's what it's trying to say, that it wouldn't be solvable, I think.
Is there an answer for it, Adam?
It just says the density of acceptors would be this, and let's see if that's what we get by doing this quickly. That would be, let's see, 2.4 times 10 to the 13 squared. Over n0.
Why are you doing that though?
Times 10 to, I'll explain in 1 second. Times 10
Okay.
to the is 1 point. Oh, which is not what they got. Did I type it in wrong? 2.4 times 10 to the 13 squared over 3.55 times 10 to the 16. And I get, these are in centimeters and centimeters. Okay, so just never mind. The reason I'm doing that is because there's just a corresponding, if that is our charge, right? If that is our density of electrons, there is just is the corresponding density of holes, which would have the same effect, right? If I say I have it,
but the problem.
Do you guys know the volume? Is the question. Do you?
We do.
I don't know. It's just, do you know the volume?
We do know the volume.
If you do, then if you have, I don't know if do you have the full table for like all of germanium, silicon? Like it has all the values for germanium, silicon, and gallium.
I've got it here. What do you?
Well, you have atoms per cubic centimeter.
Mm-hmm.
So if you know how many if you know the density of donor atoms, and you know, so the density of donor atoms would be whatever you calculated. I didn't actually look 100%, but if you know the density of donor atoms and you know the density of atoms per centimeter cube, you know how many atoms per centimeter cube need to be replaced with donor atoms.
But we're talking about adding acceptors instead of donors.
Oh, adding acceptors. Oh, then
Yeah.
that would be, you would have to find PO then first, but it should be
Yeah.
the same thing.
But I think, Adam, can you scroll back up to the semiconductor equation that you were talking about?
Yeah.
I think the reason why that doesn't work is because what we're saying there is N0 times P0 is equal to Ni. So logically, as we increase N0, because Ni is a constant, right? So if we increase N0, then P0 has to go down. That's why we can't do that, because in our equation, we started with an N-type semiconductor. And that equation, P0 is equal to Ni squared over N0, is still referring to an N-type semiconductor, in which case N0 is going to be much greater than P0,
Yeah.
so it doesn't really apply to the question. Does that make sense? At least that's what I'm thinking.
Yeah, I see what you mean. The part, yeah. Just the fact that knowing when something like that applies is a little strange. Oh boy.
That's a lot of twos.
Yeah. Don't know why I did that. Can I make it happen again? No. But yeah. Strange. I wish there was. Can we get this number somehow? So it says the
Yeah,
density
you
of
can.
acceptor. How?
So go back up to what we did for question A.
Okay.
So literally, we're going to do that exact same question over again. So RA over L is equal to 1 over E N0 mu N. And instead of N0 mu N, just do P0 mu P. Right? Because we're assuming that in adding acceptor atoms, that we don't have to worry about the concentration of donor atoms.
Oh.
Does that make sense?
That makes sense to make that assumption, and then we can solve the question. But why are we making that assumption?
Because we're adding acceptor atoms, and every time that you add either acceptors or donors, you ignore the other.
Oh, you're ignoring the other. Yeah,
Yeah.
I see. Okay, that does make sense. Yeah, because it starts intrinsic. It starts out intrinsic.
Yeah.
And then you're gonna add something to it, so you can ignore the other one. Yeah. Okay. So you'd get that number there. Yeah, that makes sense.
Sorry, so what was the conclusion? I was just zoned out for a bit.
The conclusion was just that if we did this instead, you could go through this exact same process, and you'd end up with an equation P0 equals L over R A E mu P, just like I did here for N0. Except now it's
and you're using that assumption that if we're adding donors or no acceptors, if you're adding acceptors, then you discredit the other. Okay. Okay, so then you end up with that equation.
We're starting out intrinsic. We're starting out as an intrinsic semiconductor.
Oh, okay. So yeah, so you end up with that question, that is for that final expression, and then you just get a different number.
Get a different number. Yeah.
But it would still correlate, like if you were to put NO multiplied by PO, like if you were to multiply those two values, would you still get no, you wouldn't.
No, you wouldn't get Ni squared because those are two different semiconductors that you're talking about. One has been one you've added acceptors to, and the other one from part A we added donors to.
Yeah, I guess I should really call this. I should really call this NO1, and this is PO2. So it's two cases: case 1, case 2. There is a separate NO2 which would correlate to this PO2, and NO2 times PO2 would be Ni squared.
That's interesting.
But so would NO1 and PO1 if you calculate.
If you figure out PO1. Yeah. Right? It's two cases, two separate cases. So that was confusing me too until the second I started explaining that sentence right there. And then I was like, oh, okay, I get it. But yeah, it seems like these two should multiply to Ni squared, but the fact that they're two cases means you're talking about two different configurations of this semiconductor. And so this will have its own concentration of electrons, and this will have its own concentration of holes, which is separate.
I don't understand why that's the case, but I understand the logic of it. Like, I understand that is the case, but I don't understand why.
Well, two different semiconductors, so like an intrinsic semiconductor will always have Ni squared, right? NO times, you know what I mean? The number of the two different things will always just be the square thing. But then whenever you have a configuration of it, let's say you have configuration 1, right? Then it'll have NO1 times PO1 will multiply to Ni squared.
Mm-hmm.
And then, so config 1, and then if you have configuration 2, you'd have NO2 times PO2 would be also Ni squared.
But what I'm trying to say is that,
these
say
are
in your
not
first...
related.
If, like, think about area. Area is equal to length.
Sorry. I just want to make a point that right here, how we have these two configurations. So say on your first configuration, you increase NO by, let's say, 5-fold. And then for configuration 2, you you increase PO by 5-fold. Wouldn't that mean the same thing? Wouldn't they both equal Ni squared then?
Yep.
Like if you increase this by 5, this goes down by 5.
Exactly. And then if you increase, or if you decrease NO, if you increase NO this time for your second configuration, if you increase NO, PO would go down the same amount.
Yeah.
Yeah.
So these pairs are related, but these are not related.
Oh, okay. So just so I proved
I think. Go ahead.
So because of the fact that the arrows are pointing on different variables just proves how there are two separate configurations.
Yeah, they're two separate. These are separate variables. This is not the same NO as that NO.
Yes, okay.
They're not.
But they are equal to the same Ni, or no, they're not.
Yeah, this is the same Ni. It's the same
Okay.
intrinsic. It's the same intrinsic material, but we have two different extrinsic.
Yes. Okay. Yes. This
whatever
makes
you hear
sense
say.
now.
Yeah.
Okay. Okay.
Extrinsic, is that the word? Extrinsic? Yeah.
Extrinsic.
yeah.
Okay, good. Yeah, two different extrinsic materials. Okay.
Cool.
Okay, so let's maybe take a look at what should we do. I think homework 3 was kind of the hardest for me because the semiconductor stuff was confusing, like the conceptual questions. Although actually, like the math was like the just the ones that were just like just use NO NO PO equals Ni squared. Obviously, those are simple questions. But I guess let's actually do photoelectric just because I said we go back to that. Let's start there, and then let's start there. There's only 3 questions. So this is from Survey. I do like Survey. I wish Survey had more of the stuff we're doing. It does have some of the stuff, but not really everything. Okay, so 30. So wickedly big textbook. 39.13 problems. Okay, 39.13. This is chapter 39. Yeah, chapter 39.13. Okay, so this one. And then 14. And then 41.
Also, I wanted to ask, are you gonna do another session?
I don't know. I don't really have that much time. That's the thing. Like I would like to, but I'm just very busy these next few days, so it's probably is the only one that I have time for.
Right.
Okay, let's take a look at 13 here. So the work function of a someone sent me some. So the work function for zinc is that find the cutoff wavelength for zinc. Okay, so the cutoff wavelength is so it means that we have kinetic energy equal to 0. Right? We have no kinetic energy. You just get off the work function, and so that means that the energy coming in from the light is just equal to the work function. That you just barely make it. So what that tells us is that HF cutoff is equal to that. So that's how we get our formula for the cutoff frequency. So the cutoff frequency is equal to 4.31 electron volts per, and this is, I have it here. I have a formula sheet that I'm putting together. I can share it in the chat. It's not full. Doesn't have everything. So don't rely on it entirely. I'm just adding to it as I go through the practice problems, just like whatever's an interesting equation or interesting number. No, that's the wrong one. So I just been putting this together, so I can share it. I guess I'll share it in the chat. But again, not complete. I will complete it by the time the test starts. Put it in physics chat here in case anybody wants it. Again, will be completed. Okay, so then I need to open it. Close that. I just need my H value in terms of electron volts. So that's going to be 4.1357 times 10 to the negative 15. Negative 15 electron volt seconds. And so that's just some number. 4.31 over 4.1357 times 10 to the negative 15. I get 1.042 times 10 to the 15 per second. That's part A. Part B, what is the lowest frequency of light incident on zinc that releases photoelectrons from its surface? cutoff frequency. Isn't that the same thing? Yeah. Find the cutoff? Oh, cutoff wavelength. Oops. So that's actually the answer for part B. Wavelength for part A is, so the cutoff wavelength is FC over, no, C over FC, right? So I got to do that. C in, well, it doesn't matter in what. Wavelength should be in nanometers, I guess. So the speed of light is 3 times 10 to the 8 meters, and this is 1.042 times 10 to the 5. So that's 2,879 meters? That's a huge wavelength. What? That's not, that doesn't make sense. Meters per second. Meters per second. That does get me meters. C over the frequency, 1.042. Is that the answer? That's a ridiculously huge wavelength. Light does not have that wavelength. That doesn't make sense.
They're supposed to be 287.9 nanometers.
I think I made, yeah, I think I made a I think I typed it, like, that might be, I think that's supposed to be 10 to the 15. Yeah, that's 10 to the 15. 4.31 over 4.1357 times 10 to the negative 15. Yeah, that's supposed to be a 15 there, not a 5. So then it's going to be 3 times 10 to the 8. Yeah, which is 2.879 times 10 to the negative 7 meters. Is that what you said just now?
Yeah.
Yeah, okay, there we go. Okay, and then that's the frequency. So that was the wavelength, and now that's the frequency. If photons of energy of that are incident on zinc, what is the maximum kinetic energy of the ejected photoelectron? So for part C, the kinetic energy is just the amount of energy you get from the light, right? Which is, the amount of energy you get from the light is 5.5, I'll just say E light. Okay, the amount of energy you get from the light minus the work function. So that's just going to be 5.5 EV minus the work function, 4.31 EV, which is just going to be, I don't want to mess it up, minus 4.31 is 1.19 electron volts. There you go. Okay, nice, simple question. Number 14, the work function for platinum, again, stop me if you have any questions. The work function for platinum is that the ultraviolet light of wavelength that is incident on the clean surface of a platinum sample. We wish to predict the stopping voltage, and we will need stopping voltage we will need for electrons ejected from the surface. What is the photon energy of the ultraviolet light? Well, the energy of light is hc over lambda. Ooh, that's not a good lambda. Whoa. I forgot how to draw lambda all of a sudden. There. that's how you draw it. Which is 1240 electron volt nanometers over 150 nanometers. So this is just going to be 1240 over 150, which is 8.26267 electron volts. So that's the amount of energy of light that we have coming in. How do you know these photons will eject electrons from platinum? Well, we know this because we can check the cutoff frequency, right? So the cutoff frequency is going to be the work function over H, right? So the work function is 6.35 electron volts over 4.1357 times 10 to the negative 15 electron volt seconds, right? And so we can see here that we get 6.35, 4.13 10 to the negative 15. So we get our cutoff frequency is 1.354 times 10 to the 15 hertz. I just say hertz. So if we have a higher frequency, we will have more energy, so it's fine. But if we have a lower frequency, then we have an issue, right? So you can't have a lower frequency than this. So let's just calculate what the frequency is for nanometers here. So the wavelength, I keep forgetting how to draw lambda. There you go. The wavelength is 150 nanometers. So the frequency is going to be C over over 150 nanometers, right? So that's going to be, well, it's going to be, you need to convert, okay, so it's 3 times 10 to the 8 meters per second over 150 nanometers, but I need to convert the meters to nanometers. So 1 meter has 10 to the 9 nanometers. Yeah, 10 to the 9. Yeah, that's right. So it's going to be 3 times 10 to the 17. That doesn't make sense. Is that right? I think that actually is right. So that's nanometers per second, and this is in nanometers. I think that actually is right. 3 times 10 to the 17 over 150. So that's 2 times 10 to the 15, which is greater than our cutoff frequency. So we're good. Since we're greater than our cutoff frequency, we will limit electrons. What is the maximum kinetic energy of the ejected photoelectron? Okay. So Ke is going to be the amount of energy you get from the light, okay, which is hc over lambda minus the work function. So that's going to be 1240 eV nanometers per 150 nanometers minus the work function, which is 6.35 electron volts, which is going to be 1240 over 150 minus 6.35. So the answer is 1.9167 electron. Okay, so that's the amount of kinetic energy of the electrons coming out. What would be the stopping voltage? So we just need to use a formula for this, which is, if I go back to up a little bit, which is, where are we? The stopping, there it is. So E delta V stop is equal to the kinetic energy. So delta V stop is equal to 1.9167 electron volts per electron. So it's 1.9167 volts. And that's our delta V stop. Okay. Again, I will continue on unless someone stops me. Figure 41 shows the stopping potential versus the incident photon frequency for the photoelectric effect for sodium. Use the graph to find the work function of sodium, the ratio H over E, the cutoff wavelength, all that stuff. Okay. So this is essentially our lab. So I'm not going to do everything. I'll just explain how you're going to do it, right? So the work function. So the work function is our y-intercept, right? So that right there is our work function. The ratio H over E, well, look at what we're plotting. We're plotting delta Vs versus frequency. So we got to find an equation that relates delta Vs. Well, we know E delta V S is equal to the kinetic energy, which is also Hc over, well, Hf minus the work function, right? Which that kinetic energy, so they're both equal to the kinetic energy, so we have that here. And so plotting, dividing both sides by E here, so what actually, that's actually not quite right what I said, is we got this equation. So now our slope of this, you see this is delta Vs versus F, delta Vs versus F, right? Our slope is H over E, right? So I'm going to say slope is H over E. And this is negative phi over E. Okay, negative phi over E. Okay, so if you want to find the work function, you just got to multiply by E. And then the cutoff wavelength, well, you just divide the work function by H. And that's it. So I won't do it. To do it, you probably just take, I guess you just take points. That's it. Yeah, just take points. Do they give you the actual data or no? But they give points like that, so I think you. Yeah. Okay, that's everything for Hall effect. Not Hall effect. That's everything for homework 2. So let's look at homework 3, which I think is the one that really is practicing. I guess we could also do homework 1, which is like electric stuff, but like that is kind of good to have. Let's do homework 3, and that's probably going to be the end after doing homework 3. So of course, as always, anybody stop me if you have any questions. Okay, so that's not how I want to scroll. There we go. So I want to go to 26.1. 26. Oops, 26.1. So here we go. So chapter 26, question 1. Question 6. This includes that. Oh, that looks a little rough. 13 and 14. And that's it. We're not doing Neiman ones. I don't want to do the Neiman. Okay, let's take a look at this. So this is for semiconductors, conductivity, and Ohm's law. So a 200-kilometer long high voltage transmission line, which is it's a cylinder, right? Which is 2 centimeters in diameter, carries a steady current of 1 kiloamp, so 1,000 amps. So the current is equal to 1,000 amps. If the conductor is copper with a free charge density of that, so the free charge density of electrons, that's N0, is equal to 8.5 times 10 to the 28. That's a weird 8. Oops, sorry. 8.5 times 10 to the 28. That's how many electrons we have per cubic meter. So this is per meter cubed. How many years does it take 1 electron to travel the full length of the cable? So the distance is equal to 200 kilometers. Okay. So current is how many diameter is that. How many years does it take the 1 electron to travel the full length of the table? So we got to figure out the drift velocity, I guess. Yeah, we got to figure out the drift velocity. Let me find that equation that relates that. We're solving for the drift velocity. Okay. And then we're gonna use the fact that it's 200 kilometers long, see how long that takes. So here, the current density is equal to the current per area, which is equal to NQ VD. Perfect. VD equals I over ANQ. And then from here, we just plug everything in. So 1,000 amps over the area. Area is pi r squared, right? So pi, and then it's, so I need to switch, do I need to switch this to centimeters? Meters? Yeah, I need to switch it to meters because there's meters here, right? So this is equal to 0.02 meters. So it's 0.02 over 2 squared. So r is half the diameter, times 8.5 times 10 to the 28, times the charge, which is negative. Yeah, it doesn't matter. It doesn't matter. Yeah, it's technically negative q, but that just means we're going the opposite way down the cord. But we don't, the orientation of the cord doesn't matter, the cable. 1,000 over pi. Interesting that pi shows up here, but makes sense because there's a circle in there. So 0.02 over 2, 0.01 times 8.5 times 10 to the 28 times negative doesn't matter, q, I forget q, the charge. Oh, why a 1.607, I knew it. All right, 1.607 times 10 to the negative 19. And so I get that VD equals just the magnitude, whatever. We don't need the direction. So 2 2.33 times 10 to the negative 4 meters per second. 10 to the negative 4 meters per second. And so if v equals d by t, then t equals d by v. So distance is so it's 200 kilometers. So it's 200,000 meters per 2.33 times 10 to the negative 4 meters per second. So the time it takes in seconds is 200,000 divided by 2.33 times 10 to the negative 4. So the time in seconds, whatever. The time in seconds, okay, I'll write it. 858369098.7 seconds. I want to convert seconds to years, right? So to convert seconds to years, I need to multiply by, I guess, minutes. Okay, I got to do a little bit of conversion here. And minutes to hours. So 1 hour has 60 minutes. Then I want to convert hours to days. So in 1 day, there's 24 hours. Then I want to convert days to years. So in 1 year, there is 365 days. Okay. So I just do all this. I take my answer, I multiply it by 1 over 60, by 1 over 60, by 1 over 24, 1 over 365. Okay, and this takes 27.22 years to travel the length of the coin. Let's try the next one. I know we're at 9 o'clock, so if anybody wants to get going, you get going. We'll finish soon. Just like 2 more questions, or maybe this is let's see how long this takes. Actually, this is kind of a good one to finish on because it's like one of those questions where you gotta like think about things. Obviously, that's all these questions, but you gotta think about things growing. So we have this. So figure 2. Let me just make sure this was actually assigned. 26.6. Yeah. And it gives the answers to us. So this figure represents a section of conductor of non-uniform diameter carrying a current of that. The radius of cross-section A1 is that. What is the magnitude of the current density across A1? So the current density across A1, remember current density is J, it's defined as current per area, right? So the current is 5 amps and the area is pi r squared. Right, so pi 0.4 centimeters squared. That's fine. Checking the unit. Whoops. Okay. So that's going to be 5 over pi, and then 0.4 squared is going to give me, it's going to be 9.95. And what units are these? So this is amps, which is charge per second per meter squared. No, you can just say amps. So this is just amps per centimeter squared. There, that's it. Yeah, amps per centimeter squared. That's fine. So there's the answer for part A. The radius R2 at A2 is larger than the radius R1 at A. That's not a question. Oh, never mind. That's not a question. B, is the current at A2 larger or smaller? The current is the same. Okay, so the current at A2 larger, smaller, or the same? So the current is the same. The flow of electrons, it doesn't matter here because, so if you think of a resistor as like a smaller bit of a pipe, then this would slow it down, and then it would be the same speed over here. There's nothing slowing down over here. Right? It's just a flow. So the current would be the same, but the current density would not be the same. So is the current density at A2 larger, smaller, or the same? Assume A2 equals 4A1. Specify the radius, current, and current density at A2. Okay. So we're looking for the current density. Okay, so specify the radius. So the radius at A2 is, well, if the area, so we know A2 equals 4A1. So we know that pi R2 squared equals 4 pi R1 squared, right? And then I'm trying to find R2 over R1, right? So that would, well, the pi's are going to cancel, right? And so R2 over R1 is equal to 2. If I just square everything, right, it looked like that. And then just take the square root of everything, you get 2. So R2 is 0.8 centimeters, right? The current is going to be the same. Yeah. So that's for part D. Current is still going to be 5 amps. Current does not change based on the size like that. Right? And then current density will change. So current density, part F, we're looking for J, right? Current density, which is the current per area 2, which is going to be I, which is going to be 5, same process. It's going to be 5 amps per pi 0.8 squared, pi r squared. So 8, I get my current density is 2.5 amps per centimeter squared. Ah, I'm off by 10 to the power. Oh no, because never mind, because they do it in meters. Yeah, that makes sense. Okay, and I think that's probably a good question to leave it on. There we go. That's the end of the session for today. That's the last question I'll go through. I got some work I got to do before I go to bed tonight, so I better get going on that. But hopefully this was a helpful session for everybody. I enjoyed doing it for sure. Nice to talk to everybody. And yeah, so I'll be here for a couple more minutes in case anybody has any questions. Other than that, have a good night.
Thank you.
Goes well. No problem. No problem.
Also, I wanna ask you something.
Yeah.
Like if I'm able to do all the homework questions and like the textbook questions, like do you think that would be enough?
That's how I always do it for physics. Is I just that's all I really do. I mean, I type notes, which is helpful for me, but I don't know if that's helpful. That's obviously that's not helpful for everybody. But for me, it's helpful to just like type my notes and then do all the practice work, and that gets me by fine. So yeah.
All right, thanks.
Yeah, no problem. No problem.
By the way, thanks, Adam. Good luck to everyone though.
That's good. No problem. Good luck on everything.
Adam?
Yeah.
I don't want to take up more of your time, but I just have one question.
Sure, no problem. Ask whatever you want.
How have you been studying for 328?
328 of type my notes. So if you know, of course I type my notes. And then other than that, how have I been studying for 328? Yeah, that's a good question. Just like I guess I've been really just trying to keep up with lectures because I've been falling behind a little bit in lectures because I had some internet issues in the past few weeks, and so I couldn't watch some lectures, so I've been falling behind there. I did a little bit of practice work. I don't really do the practice work by myself, but sometimes when I'm talking to people, we do a couple of the practice problems together, so that's sort of tested there. Yeah, I really should do more work. I'm not a really good person to ask for advice on 328. I'm not really super behind in the content, but I'm behind in practice for sure. I don't practice barely anything.
Okay.
But I should.
Like,
that's not good. I should.
Yeah. It's just I've been doing like as many practice ones as I can, but like nothing sticks. I do the question, I move on, but I don't really remember how to do it.
Yeah, so I think maybe worth your time more to spend like maybe reading the textbook or watching some videos online about it than doing practice problems. Because for me, I feel like everything's sticking fine. That's why I'm not really stressed about it, because I feel like I understand everything from the lectures. So maybe for you, it'd be worth more of your time to first look at review lectures or read more of the textbook, or if that works for you.
All right. Thanks,
That's
Adam.
my advice. No problem at all. No problem.
Bye.
Okay. Have a good night. Good luck on everything.